All right, we're back. We're on page 2 of note 16. We're talking about applying the fundamental theorem. It's a big deal. And so on this page, we're going to evaluate using the fundamental theorem with proper notation. So notation is a big deal in calculus. And then we're going to verify using geometry if possible. It's not always possible to do geometry. It's also like sometimes really challenging to do the fundamental theorem. So like don't get the impression that one is necessarily better than the other, although the fundamental theorem is probably definitely better. All right, so first, I need an antiderivative, 1/2 x squared. We skip the plus c because it's just going to cancel itself out when we do f of b minus f of a, such that 0 to 3. All right, so I'm going to give you two options for doing this. Option 1 is we do 1/2 of 3 squared minus 1/2 of 0 squared. Option 2 is that we do 1/2 and then we do 3 squared minus 0 squared. I kind of prefer option 2 because I feel like I mean, you get the same answer either way, but I feel like it's a little, you're less prone to make a mistake that way, let's say. So I think you should do that, but you know, your call. So I get this. On the other hand, all I'm really doing is finding the area from 0 to 3. So 0 to 3, I need this, but that's just half of 9, 1/2 of 9. So 9/2. So you get the same answer either way. Geometry is probably easier, but let me tell you, once you learn the fundamental theorem, you're probably never going to think to use geometry again. It's kind of sad, but also probably the case. Here, all right, we need an antiderivative. And we're going to go from -1 to 4. So I'm going to do 1/2. And then I'm going to plug in 4. So 4 squared minus -1 squared. So that's 1/2 of 16 minus 1. 1/2 of that. So, I mean, 15 halves. 7.5. However you want to think about it. Okay. So fundamental theorem, you just go for it. You're never really thinking about what the graph of y equals x looks like. You don't really care. Over here, when we go from 1 to 4, we have to worry. And so the reason we have to worry is that part of this is negative and part of it's positive. So like our first triangle has an area of -0.5. Our second triangle has an area of 8. So overall it's 8 plus -0.5, which is 7.5, which is in fact 15 halves. Same answer, but this one geometrically, it's more thinking because you have to like work out like what regions are positive, what are negative, so you can do the total accumulated signed area. Over here, fundamental theorem does not care. Fundamental theorem's like, okay, let's do f of b minus f of a. Let's just find the displacement. Who cares about like how it went about doing that? So that's an advantage, I would think, for the fundamental theorem. Let's try this one. So I need an antiderivative. So that's going to be x squared minus x. We're going to go from not negative, from 1 to 3. All right, so that's going to be, first we plug in 3, and we get 9 minus 3 minus quantities. So this is, I think that's the best thing to do. When you plug in, when you do f of a, if it's complicated, so the previous ones weren't really complicated, they were just like kind of one and done type deals. Once it gets to be a little more complicated, f of b, put it in parentheses, minus f of a, put it in parentheses, and you will make far fewer mistakes. So this should be 6. All right. Geometry. What are we doing? 1 to 3. Not bad. Just trapezoid. So it's going to be 1/2, 2, and then 1 plus 5. So 6. So same answer. You'll always get the same answer, provided you can do it. The issue is you can't always do the geometry. Let's look at this one. All right. 1 over 1 plus x squared. I have that memorized. If you don't have it memorized, this is one where you're just like in trouble. 1 over 1 plus x squared is arctan. So we're doing the inverse tangent of x from root 3 over 3 to 1. I would say, by the way, if you're not really sure, I think this bound is kind of a tip-off that there might be an arctan involved, or a tangent at least, because radical 3 over 3 is the tangent of something. Like if I saw radical 3 over 2 and I didn't know what I was doing at all, I would think like radical 3 over 2 is definitely related to sine and cosine. So maybe there's a sine or a cosine hanging around here somewhere. In this case, radical 3 over 3, that's the tangent of something. So maybe there's a tangent, an arctan, something hanging around. And in this case, there was. But now you got to remember your arctan. So it's the arctan of 1 minus the arctan of root 3 over 3. I think on the AP exam, you could probably leave that. I don't trust that rule. I feel like at any moment they could flip on you and be like, nope, we don't do that anymore. So the arctan of 1, tangent of what is 1? Well, pi over 4. Root 3 over 3 is the tangent of pi over 6. So pi over 6. And then you get, I don't know, 6 minus 4 is 2 over 20, pi over 12. So pi over 12 is my answer. Do you think that geometrically I'm going to be able to get that like in any feasible way? Absolutely not. What is root 3 over 3? I don't know. It's like maybe here. And then to here. Like this area? Are you kidding me? Like, I have no idea. But it turns out that it's pi over 12. And if you don't have the fundamental theorem, like there's no chance you're going to be able to do that. So this is a really good example where like fundamental theorem wins the day. Geometrically, like draw it and you're like, I don't know. It's that, right? Like probably a little more than something, a little less than something else. I really have no idea. Okay, so these we just want to use a fundamental theorem. So I'm just going to do these. Proper notation throughout. 3 halves t squared plus 2t negative 1 to 3. So this is sufficiently complicated that I'm going to do 3 halves of, I'm just going to do this plus 2 times 3, 6. Why are we overdoing this? You know, it might be better, in fact, to like simplify as we go, but whatever. 3 halves minus 2. So there's kind of a thing you can do that will happen like a lot, right? So what I'm going to do is I'm going to do this minus this, and then I'm going to do this minus this, and then combine those. That can speed things up for you in like weird ways, right? So 27 halves minus 3 halves is 24 halves, which is 12. So that comes from those two calculations. And then 6 minus negative 2 is 8. And that comes from the purple things. And so overall, I'm getting 20. And we could check that on a calculator if we wanted. It's also, is that a trapezoid? I think it is. You do 1/2, 4, plug in negative 1, and you get negative 1. Plug in 3, and you get 11. So you get 2 times 10, so you get 20. So if you can check them geometrically, do it. If not, don't. This one, your life is easier if you always use negative rational exponents instead of leaving things in denominators. Like this. So plus 1 times the reciprocal, negative 1/2 x to the negative second, 2 to 4. So I'm going to do negative 1/2. And now I'm going to do 1 over 4 squared minus 1 over 2 squared. So the negative 1/2 will distribute, and that's why I did that. Negative 1/2. What do I get? 1 minus 4 is negative 3/16. So I get 3 over 32, which makes sense to me because 1 over x cubed is definitely positive on the interval from 2 to 4. So like I should get a positive when I do it. All right, the derivative of cosine is negative sine, so this should be negative cosine from 0 to pi. Watch out for the cosine of 0, man. It's there to mess you up. Minus, negative. It's like everyone's always like, oh, good, plugging in 0. When you plug in 0 to most things, you get 0. Not when you plug it into cosine. This is negative, negative 1, so that's positive 1, and then minus negative is plus cosine of 0 is 1. So we get 2. I would like to point out the geometry of this, right? That is sine from 0 to pi. So sine from 0 to pi is like 1 hill of sine. This has an area of 2. Exactly 2. What? Isn't that weird? I think that's like a very strange thing. So I don't know. We're done with this page. We've fundamental theoremed quite a bit. You could check all of these, and I encourage you to, on your calculator. Just punch in the definite integral. I am not going to do that on the video. I'm going to stop it here, and I will come back in the next one and do some more. So I will see you there.